Alright, so what we're looking at in this particular recording is, again, Lenz's law, but how does it apply to solenoids? So a solenoid is basically a curved wire conductor. So if I kind of draw it out, a solenoid would be an object that sort of has an iron core, and then you have some wires wrapped around it. So our question is, how do we use Lenz's law and Faraday's law to explain the current that gets induced into these kind of objects? So that's what we're looking at. If you look at Lenz's laws in coil, it all has to do with whether or not you have seen a change in magnetic flux. So if we have a look at scenario A, if we move it to B, you can see in terms of the density of the magnetic flux or the magnetic field, there hasn't been a difference. So there's no change in density. So in this scenario, you won't get a EMF produced. That's basically what Faraday told us. Faraday's law states that we only generate an EMF, so some kind of energy, if there is a change in magnetic field density or magnetic field at all flux. If we go from B to C, you can actually see that it actually gets less in flux density. So according to Faraday's law, yes, you do get EMF produced because we've gone from a highly dense magnetic field of B to a lower density field of C. Okay, if we go from D to then E, you get no EMF there. As you can see, that's still the same magnetic field density. If we go from C to D, again, there isn't any magnetic field induced. Or actually, yeah, there's no EMF produced there. Okay. When it comes to applying our rules for Lenz's law, just remember when dealing with solenoids, so if we have a solenoid that looks somewhat like this, so we have a solenoid and we have wires. Now to do this, you will need to apply your right hand grip rule. Oh, keep drawing my left. So your right hand grip rule, your fingers around like this. The direction of your thumb is the direction of the B field. Usually I like to say that's also the direction of the North Pole. And also your fingers act as the direction of the current. And we need to make this very explicit. It is the conventional current or the positive current. That's what we're looking at here. There are some general rules in terms of applying Lenz's law and using the right hand grip rule. If you see a magnetic field out of the page decreasing, your thumb needs to point out of the page. What that basically means is if you have less if magnetic fields coming out of the page are dropping, you want more going back out. Okay, because the idea of Lenz's law is to counter the change of anything. It's quite similar to Newton's law in that regard, but it's to counter the change. That's how we counter the change there, and we will show some examples of how that counters. If magnetic field out of the page is increasing, then you want your thumb pointing into the page, so you want to repel the increasing amount of magnetic fields. If magnetic field into the page is decreasing, thumb needs to point into the page. And if the magnetic field into the page is increasing, it'd be the same thing as saying according to Lenz's law, our opposite desire would be to decrease into the page field lines. So to decrease the amount of magnetic fields going into the page, it'd be equivalent of producing more magnetic fields pointing out of the page, which is the same thing as saying thumb pointing up or out. Okay, so let's use this example here. We have a North Pole, and we know that for magnet, it always goes from north to south. So in the first one here, we have North Pole magnetic fields coming into the page like that. And if we look at what's happening here, the magnet's coming further down. So it's almost the same thing as saying that as it comes further down, there'll be more exposure of magnetic fields going into the page than out of the page. So as the North Pole's coming down, you can imagine that there is more magnetic field lines going into the conductor. So let's point that's the original motion, yeah? So that's our original B field motion. What's going to happen here, according to Lenz's law, is I'm going to generate a magnetic field that opposes this. So if I'm generating more field lines going into this conductor, Lenz's law states I would generate more magnetic field lines coming out to repel it. Okay? So that's our induced. So if it's coming out of the page, if you use your right thumb, your thumb is pointing out and your fingers, okay, kind of wrap around in a anti-clockwise direction. So the induced current is going anti-clockwise. Okay, let's look at example in the middle. Let's also look at what's happening to our field lines. I'll use a lighter color just so it's a bit easier to track. Okay, so it's a south pole. If it's a south pole in the perspective of our conductor, the magnetic field lines are coming out the page. Okay, as we get further and further away, so as I'm pulling this magnet away, there is less connection between the poles and the conductor. So I actually get less magnetic field lines coming out of the page. So initially we had 3. Now let's say instead of that, we only have 2. And then I'll just dot this to say that once upon a time there was 3. According to Lenz's law, we don't want that. We want to oppose that to get something back. So in order to go through this, so because we're reducing the amount of magnetic fields coming out of the page, Lenz's law states that whatever induced EMF we create, it's also going to generate magnetic fields coming out of the page here. Okay? Because the original motion or the original force of motion meant that we had less, in this case, less B fields, let's say going this way. And so Lenz's law says, no way, we want to counteract that. So we're going to also generate magnetic field lines going in that direction. So using your right hand grip rule, thumb pointing up, fingers are going around the circuit in this orientation. So it is also going to be anti-clockwise. The last example we have here is a North Pole going away. So a North Pole is going, let's just draw dotted lines for this. North Pole is going into the page. As we bring it away, we have fewer lines going in. So instead of having 3 bolted lines, I'll have 2, like that. Okay? So according to Lenz's law, I want to counteract this change. So the change we have here is less B fields going down. So according to Lenz's law, whatever induced current I'm going to produce will generate magnetic field lines to oppose the original change. Hence, I'm going to generate more field lines going into the page like this, or going down, sorry. And if I use my thumb, right thumb that is, pointing downwards, my fingers are curling in the clockwise direction. Hence, the induced current is going to go clockwise. That's how you do that one. Let's have a look at an example where we are using the solenoid. So let's look at example 1 here. We have our magnet going into the solenoid, so going in like that. If I push this north pole further in, I'm going to induce more lines going into my solenoid like this. Okay? So the B motion that I'm creating, the original motion I'm creating, is going this way. So according to Lenz's law, the induced magnetic field, the B induced, would oppose this by going this way. Okay? So if that was to occur, if you use your right hand grip rule, thumb is pointing to the left. My fingers are sort of wrapping on or over the solenoid. So the current is kind of going up like this. And then it comes around to this. So here it goes from A, G, and then B. If I track along next to question B, we have our south pole, and that is originally coming out of the page. Okay. What happens when we pull it away from our solenoid? We pull it away, we have less field lines coming out of the page. So it goes from that to dotted to just 1 coming out. Okay. So what's happening here, you can see, is we have less field lines going to the left because of this change. So according to Lenz's law, the induced magnetic field should also point to the left, because that's the only way I'm going to recreate what I originally had. So that follows from A, then it also goes to A, G, B. Okay, and I will check the answers in a second because these ones do trick me as well, so we'll see if I am correct or not. C, we have a magnetic field going into, or a south pole going in the page. So that's what we get there. Now the original motion is going closer to X, which means that I am going to generate more field lines going to the left of this example. So as this goes across this way, I'm going to generate more fields popping out, or getting more concentrated in there. So the B motion, the original motion, is to produce more field lines going in that direction, which means according to Lenz's law, the B induced, or the induced direction of the magnetic field, would oppose that. So our induced magnetic field is going to oppose that motion. It's going to go this way. So this is going to be north here. That's going to be south there. I'll just show the examples for the other ones. So what that means is the current is coming down like this. So it goes from B, G to A. So the induced current goes in that direction there. Okay. The last example we're going to go over is the North Pole. So the North Pole is originally going into the page, but as we move it further and further away, so we're going to drag it out, there is fewer lines going into the page. Okay, so based on that motion, that's going to induce an EMF, and according to Lenz's law, we're going to induce a magnetic field that will try and increase the amount of flux going to the right here. Okay, and that will also see us get a similar thing over here. Okay, so there's that. By moving our magnet, so if we move our magnet, we cause a change in flux over time, and that produces an EMF. This is Faraday's law. Okay, and that's what Faraday told us. The thing that we can learn from this is then the negative of Faraday's equation, and that is Lenz's law, which says that the EMF we produce will produce a current that produces a induced magnetic field that opposes the original change that caused it. And so there are the answers we have there, which are exactly the same as the ones I have here. So hopefully that helps explain how to do this question of Lenz's law in solenoids. If you have any other questions, let me know. And also there are some playlists to this particular module if you need as well.